Okay, good afternoon, everyone. Let's get started. So today we are going to switch gear to talk about quantum machine learning, and will be taught by Henry. Let me give an introduction of Henry. Henry is a final year PhD student from our group. He joined MIT in 2018. He's been spending 6 amazing years, super productive. He first worked on efficient transformers and large language models. For example, he developed several efficient method such as hardware-aware transformer, HAT, which we talked about in the earlier of this lecture, and also the token pruning, head pruning, progressive quantization, widely used actually in recent LLM research in industry. He also designed the Spartan accelerator, which remember we talked about the Spartan accelerator, to look at the sparsity in the token dimension by looking at the attention map. If they're small, then we prune the whole column. That is actually the most cited paper in the last 4 years of the HPC conference. And recently, in collaboration with NASA, he also taped it out as a chip, the Spartan chip. And later, Henry worked on quantum in an intersection between machine learning systems and also the quantum computer. His work tried to solve the problem of the scalability, how to make it scalable and reliable for the quantum computer systems. He proposed several cool techniques for reliable quantum program design and also compilation, such as the quantum NISQ, which Henry is going to introduce. He also worked on some transformer-based hardware fidelity modeling and also quantum error correction decoding. He also developed this Torch quantum library for quantum computing in PyTorch, which has been integrated by IBM Qiskit, NVIDIA cuQuantum, and also the PyTorch ecosystem. Henry got several awards, like the first place award in the ACM Student Research Competition, the Best Poster Award at NSF Institute, the Best Demo Award at DAC, first place award at Quantum Computing for Drug Discovery at SECAD. So Henry is pretty passionate for teaching. So for today's lecture, let's welcome Henry to talk about machine learning and quantum computers.
Yeah, thank you, Professor Han, for the nice introduction, and thank you for coming. And my name is Henry, so I'm currently a final year PhD at Professor Han's group, and I'm very glad to introduce a little bit about how can we use quantum computers better, and also how can we use them for machine learning tasks. But before that, this lecture we're going to introduce some basics of quantum computing. So today we are going to introduce several points. Firstly, we are going to cover the single qubit states and gates, and also multi-qubit gates, and also how can we construct a holistic quantum circuit, and also what is the current noisy intermediate scale quantum era, or the NISQ era, and also some compilation problems. And also we are going to introduce some example workflow on the superconducting quantum computers. So let's get started. So here is a really nice introduction. Here is a really nice summarization of the previous years of the development of the quantum machine. So we can see that back to 20 years ago, we firstly have the quantum machine in 1998, where we just developed 2 qubits. So that's a really small system, and we don't have to do any optimizations automatically, because we can manually design all the compilations, all the schedulings, and also all the pulse signals just by hand because of the small scale. And you can see that it takes around 20 years for the physicists to actually develop a scale from like 2 qubits to a system with over 10 qubits, right? So we can see the first 10 qubit machine is developed around like 2018. We have an IBM's machine with like 49 qubits, and also the real acceleration of the development on the hardware actually just happened in past 3 years. So 3 years ago, like in 2019, people have access to like 50 qubits machine, and we just scale from 50 qubits to over 1,000 qubits. So just a month ago, the Item Computing, which is a startup company in Colorado, they released this quantum machine with 1,181 qubits. So that's 2 orders of magnitude in just 2 years. So we really see this large and accelerating trend to develop larger and larger quantum machines. And IBM is also going to release the first quantum machine with over 1,000 qubits. So we can see with over tens of the qubits and even hundreds and thousands of qubits machine, we cannot do all the optimizations just manually. So we have to develop some ways to do the compilation and also to design the program and algorithms automatically using some smart tool chains. So with several different technologies, for example, the IBM's superconducting and also Google's superconducting chip, and also we have the chips from IonQ, which is using the trapped ion to control the ions in the linear trap to do the computations. And also finally, we have the atom computing. Basically, they use the neutral atoms, and then in the chamber, which we have vacuum chamber, and then we can control all the qubits with lasers. So we can see many different technologies. Just like 70 years ago, people are debating whether we should use a vacuum tube or we should use like transistors, right? So there is a blossom of different kinds of technologies, and all of them have hold strong promise to scale to even larger machines. So we don't know which one is best yet, but we can see a competition between them, a very interesting competitions. And also, for example, what is you may ask, like why we should care about quantum, right? So today's GPU is very, very good, right? So CPU systems, they are very mature, and why should we switch gear to emerging technology given they are not very reliable and not very mature? So I think the major source of the hope that we can use quantum is that the quantum computing has this very nice exponential speed up trend, or you can call like the first exponential is come from number of qubits. So we already see that in the last several years, we see an exponential increasing trend, especially in the last 3 years. We scale 2 orders of magnitude. And also another layer of exponential increases comes from the computing power from the qubits. So because as long as we have n qubits, and then we have actually a space with a size of 2 to the power of number of qubits. So that means we can, on the time scale, we can exponentially scale the number of qubits because of the device improvements. And on the computing power side, we also have another layer of exponential. So that's a doubly exponential rate of the potential computing power delivered by the quantum machine. So because we know that there is a widening gap between the data and also the available computing power in all these computer systems. So each day we generate about 2.5 quintal byte of the data, which is 2.5 times 10 to the power of 18, right? So, however, that large number of information can just be stored by 64 qubits. So it's a really efficient and really small number of qubits. We already have 64 qubits 3 years ago, and say if you have access, you may just log into the IBM's quantum cloud, and then you may access to a quantum machine with 127 qubits. So what does that mean? That means just with 100 qubits, we can store the information of 10 to the power of 30. So that is 1 billion years of all the human information generated, 1 billion year at the current stage, at the current speed. So that means actually quantum could be the ultimate solution for the computing power. So we can because with one more qubit, we can double the computing power. So it's not just like a linear increase. Say we have maybe I have a cluster with 10,000 of GPUs, but maybe it takes another 10,000 to double the computing power, right? But for the quantum, you just need to add one more qubit, and you have to develop some smart algorithm to fully utilize the space that the one more qubit is introduced to the system. So that's really hold a very strong potential to provide us an ultimate solution for the efficient and also scalable machine learning computing, as well as the computing for other exciting scientific discovery domains. So in order to know how should we pursue that, we may have looked back to the history to get some wisdom from our previous generations of researchers. So actually back to 1980s. So actually that's the first concept. The concept of quantum computing is just introduced by Professor Richard Feynman at Caltech. So his famous saying is that since the world is quantum, why won't we just use some quantum computer to simulate the actual quantum world, right? So back at that time, many of the theorists and also physicists, they are proposing a lot of very smart and very beautiful theory on how to use quantum computer. For example, we can, just as we said, we can use a quantum computer to simulate actual quantum systems. So many of the important systems are quantum systems. Say we want to do some chemistry simulation. We want to know what is the interactions between all the molecules and also all the items in the molecule. So in that case, we need that's actually a quantum system. And if we are using a quantum machine, we can capture all the interactions between those basic elements of the quantum system, and then we can just evolve the quantum computer to reach a final stage. And we don't have to do the simulation classically. We just use a quantum as a surrogate for the actual system, and then we can obtain the final stage, and which is very efficient. So another trend is that actually another trend is led by a factoring algorithm and proposed by MIT professor Peter Shor at the Department of Mathematics. So this trend, this line of research is that we probably can find some hidden structure, right, in the computing algorithm, and then we can leverage the exponential increase dimension to match with the hidden structure in the algorithm, and then we can use the quantum machine to solve this problem. And the factoring algorithm is a very good representative of that kind of quantum algorithm. And with this factoring algorithm, we can crack a very large integer number with very high efficiency. So the large number factoring problem is actually the foundation of today's cryptography, because all the RSA algorithm, they are building on assumption that very large number of integers are very difficult to factor, and is however with this algorithm, maybe you may ask like whether tomorrow a quantum computer will break my bank account and steal all my money, right? So rest assured that will not happen tomorrow, because of the first of all, the quantum machine are not very reliable, and also the size of the quantum machines available is also not that large. So the factoring algorithm may take around 1 million qubits to do some meaningful tasks. But that's the hope, right? That's already the impact of quantum, where many of the cryptography researchers, they are switching from the RSA to other quantum safe encryption algorithms. So that's the first trend, where the very important part of that trend is that all the researchers are trying to assume like the quantum computer is perfect. There is no noise in a quantum machine, and we can always achieve the perfect computation calculation with the machine. And also we assume that they are very large in terms of the size, but that too doesn't happen very easily. So you can imagine the real quantum machine can be impacted by a lot of different noise source, like the cosmic ray and the imperfect control. So it's very difficult to achieve the strong assumption of the noiseless, right? So that's how like 20, 30 years ago, people try to pursue just purely theoretically advantage. And then something very exciting happens in 1995, where we have some papers theoretically prove that actually say you don't have to use a really like a perfect quantum machine. The noisy ones can also do the job, as long as you do use some error correction code. Actually, that already happens in our classical computing, right? So in the classical like memory and classical communication, you already use a lot of ECC code to make sure the information you're trying to send and also trying to receive is robust to the noise of the environment. So that's also the case in quantum. So back to 1995, there are multiple quantum error correction schemes proposed, and they are basically saying we can trade the redundancy for better reliability. So just like a simple example, I send you a 1 bit, and then maybe there are some noise, and maybe I can send you this bit for a repetition of 10 times. And then you receive the 10 bit, and maybe some of them are still the original one. Some of others are flipped because of error. But as long as the error is not that large, it's not flipping over 50% of them, you can still do a majority voting to recover the original information, right? So that's also the intuition behind the quantum error correction code. As long as we have a larger scale of the system, we can trade the redundancy for better reliability. So that is the theoretical proof back to 1995. However, we still suffer like the large scale quantum machine, which means we still need to build a very large machine to achieve those advantages. So if you come to you have this 20 years ago, you have this very nice theory, and then you come to a VC and you tell them, you give me $10 billion, I can build you a 1,000 qubits machine with fault tolerant. Maybe you can get nothing because that is too aggressive. And so the scientific discovery and also engineering that happens gradually. So that's why 20 years later, people finally build some machine that is not that large, but intermediate scale with tens to hundreds of qubits, and people trying to show some advantage under this stage, trying to make sure this technology can already generate some values, no matter how large or how noisy it is. So right now we can see some recent papers like from Google back to 2019 and USTC's 2020 photonics paper, and also Xanadu's paper last year. So they try to show some experimental advantage of using this quantum machine over the classical ones. So, however, whether that advantage is practical is also questionable. So that I put a question mark there. So that means all the operations they are trying to show is actually not something very useful in the applications. For example, they are doing some boson sampling, but that is may not generate or may not useful for any existing computation tasks. So, looking back to this 20 or 30 years of the development history, so it's pretty clear that we have two paths forward, right? So the first is that we just use the current machine, like the current noisy intermediate scale quantum machine, and we try to use this bare metal in a bare metal format, and then we try to find some smart algorithm to prove some advantage. So that's the NISQ computing. And another is that we follow the wisdom of previous researchers to continue to push the frontier of the quantum error correction, which we will also cover in the later lectures. So the quantum error correction, we need to develop hardware support and also architecture, algorithm, and error correction code support for them. So that's the two main line of research currently, and both of them are we will cover both of them in the later lecture. So before we go into the those exciting advantages, let's just have some knowledge about the basics of the quantum, right? So you may ask, what is the basic of the quantum computing elements? So that is called a quantum bit, or it's called a qubit, right? So imagine that you are doing some operation on a classical computer. Actually, you are controlling the CMOS, the transistors. You are applying some voltage on the gate, and then you are doing this switch basically for a CMOS transistor. So if we consider that a very low level on the quantum side, it's also the case. So say you have a quantum computer or quantum bit, and then that contains some of the state, right? The state, you can manipulate the quantum state by applying some operations to the qubits. So in order to understand what is exactly the state is representing, we are using some mathematical tools to represent the state. So here we are calling this called a state vector, because the it actually can be described by a vector of the of all the informations of the system. So just like this, we are developing this classical system, car running on the road, and we try to know what is the current state of the system, right? So imagine if it's just one dimension of the road, and then we can just use a number 4 to represent all the information in the system, because the car is right now at the 4, right? And then also the qubit state actually is a little bit different from that, because the car can be simultaneously at different positions of this one-dimension system. It may be at this 0 state or at some other 1 state. So we have inefficient in the classical domain to represent the information, because here we just have one possible information to represent at one time, which is a one-hot vector, right? So here, just a little bit of notation for the qubits. In the qubit state, we have this classical, say A plus 0 and A plus 1 as the basis. And then in a quantum, maybe we also want to have some basis to represent information, right? So here we are also using this orthogonal and orthonormal vectors, the 0 and 1. So we are also using this called bracket notation. So brad means a vertical line here, and the cat is a line like a larger like a symbol, right? So just like this, the bracket notation is also called the Dirac notation. So we have these two states. The first is 0 state, which means it's 1, 0 as the vector formation. And also we have the 1 state, which is 0, 1. So if we are representing, just like we said, if the car is at different locations with equally probability, we can also represent the state with a more complex state vector. So for example, a qubit state can be like this, like 1 over square root of 2, and then I over square root of 2. So this is the information that's stored in one single qubit. So just try to reiterate that. So if we want to represent all the information in just one qubit, we can simply use a vector with 2 numbers, right? And each of the number is a complex number. So that can capture all the information of the quantum system just with just one qubit, right? Okay, clear? So okay, so you may ask that how can we write this in the format of the combination of 2 states, right? So actually we can do some decomposition of this to the combination of previous 2 basis states. So because as we introduced previously, the 0 state here is actually 1, 0, right? And the 1 state is 0, 1. So if we want to represent this new state in the combination of 2, we just have 1 over square root 2 of the 0 plus I over square root 2 of the 1. So this is some notation or a very special property of the quantum system, because that creates some superposition of 2 states. Because imagine in the classical domain, we only have a 0 plus 1 or 1 plus 0 at one time, because there is no way to have a bit 0 and bit 1 together. But in a quantum state, we can have a superposition because we have the energy for each of the state here. So and superposition mathematically is defined by this linear combination of the 2 basis states. And you may ask, like, okay, so right now we have this qubits with those 2 states, right? And then, but if we just want to understand what is the if we want to measure the qubit to obtain some classical bit, so the actual quantum information will collapse to either 1 and 0. So that may be difficult to understand. You can consider that you have a coin, and then the quantum system is always a coin that is rotating on the table, and it has some probability to, when it stops, it has some probability to have a heads up or tail up, right? So that's similar to when you measure qubits to the classical system, classical state. So for example, here, when we want to measure a state in the prepared state X, we can perform this computation like Px equals to this X and phi and the square root square. So here actually the X is the row vector, and this cat is a column vector. So for example, we can represent the column vector here as this column A state as the column vector, and also we have this spread as the row vector, right? So together we have this bracket notation, and then we do this computation to obtain the probability that we measure a system to 1 or 0. So here comes a little bit some math here. So basically, the X can be any of the state, right? And then say what is, if we measure this qubit, what is the probability that we get a 0, and what is the probability to get a 1? So that's similar to, like, you just stop the coin, and then how many times, or what's the frequency we get a 0 or a tail up or a head up, right? So we can do this computation where we do this make a vector multiplication between the 0 state and also the Q0 state, and then we can see that actually this computation can goes all the way to 1 over square root of 2, and then we can have a to compute the magnitude of 1 over square root 2. That means that gave us 2 over 1 over 2, 0.5 or 50% of the probability to measure a tail up. So that means if you just prepare the state in the 1 over square root of 2, 0 plus I over square root of 2 of 1, and then when you measure that, you have 50% of probability to measure a 0, and then another 50% to measure a 1. So in that case, what is the intuition behind that? So say, if we want to know the information inside these qubits, we just need to prepare the quantum information for 1,000 times. And then we measure that for, say, 1,000 times. And then you can see around 500 times of the state will be 1. And another 500 times of the state will be 0. And then you do some post-processing. And you know that, oh, previously, there should be some combination between the 0 and 1, right? And if we want to know the exact number, like say whether that is 1 over square root of 2 or is I over square root of 2, we can do the measurement on different bases to fully reconstruct the quantum state. Okay, so another property is that all the probabilities should add up to 1. So that is easy to understand because we just have 2 states. And a mathematical proof is that when we do the measurement of a state in itself, so that should be 1 because you measure a state and then you should always keep the state. And then if we just doing this calculation of this line, and then we can see that actually the alpha square plus the beta square should be 1. So that means the 2 state, the alpha and beta in the vector, they should have the property that the magnitude square of the magnitude of them should sum up to 1. Okay, so besides this 0 and 1 state, sometimes we can also measure on the other state because 0 and 1 are just 2 special states in this whole space, right? And there are infinite pairs of the orthonormal bases, and we can during the measurement we can based on the algorithm we want to do or based on the actual quantum device, we can select one of the orthonormal bases to do the measurement, and then after the measurement, the state will choose one of the 2 basis state to collapse, right? So say we measure in the 0 and 1 basis, and then if we obtain 0 with 50% probability, and then the state will just collapse to 0 state. And if we are measuring on other bases, and then they will also choose one of the 2 bases to collapse to 2. Yeah. Okay, so another thing about the quantum is I want to introduce about is called global phase. So say you just measure 1, measure 1, and then if give the 1 state will give you a 1 with 100% of the probability because you just prepare a classical state 1, right? But what happened if the state is I1? Actually, mathematically, it can be represented by this vector like 0 and I. And then if we do this calculation of the state when we measure a 1 here, actually the I will disappear, and we just take magnitude. We can see that actually the I1 and 1 are equivalent in terms of the physics measurement, right? So that means because we always need to interact with the qubits to do some physical measurement. So that means the I1 and the 1 are actually equivalent in terms of the physical measurements. So we don't have any way to know whether the system has a global phase or not. But actually that doesn't hurt the algorithm construction. So we don't have to worry about this additional global phase. Okay. So another important thing is that we have this observer effect. So that means when we measure these qubits, so we always certainly know what is the state of the qubit. So for example, we assume the qubits is in this alpha 0 and beta 1, right? And then we already know that the alpha square plus beta square should add up to 1. And then if we measure this, right, we measure on the 0 and 1 state, and then we obtain 0, and then the whole system will collapse to this classical state. So that's why typically we just have this measurement at the end of computation, because if you do that in the middle, and then everything will collapse, and then you will not get any meaningful result. So that is also very different from the classical computing. So say in the classical, we have a lot of different verification algorithms, and those verifications will check all the intermediate state of the classical computing to make sure. Say when you write something like assert in the Python, right? You are comparing this classical register to another classical register. So however, that is very difficult for quantum. So say if you are just want to check whether your qubits is in this 50% of 0 plus 50% of 1, and you cannot do that directly in a quantum because you cannot do the measurement of the system. So how can we protect information without perturb or without collapse the system? So that's the quantum error correction code task. So basically, we can just check the parity of them without knowing all the information. So we introduce that later. So another thing is that actually, when we measure multiple qubits, we can obtain, of course, we can get a series of classical bits because we have, like, say, many qubits, and then we just get the one of the classical bit corresponding to each of them. Okay, so another interesting thing, maybe the most famous thing, is the Schrodinger's cat, right? So let's say, like, if you have this cat in the box, and then you have some poison here, and then you have a laser which have a probability to generate some radiation to trigger this switch, and the switch will have a hammer to break this bottle to release the poison, and then if with 50% probability this is triggered, and then the cat will be dead, and then if it's not, then it's alive. But you never know before you do the measurement, because it's like the state of the quantum, like the radiation source there is in a quantum superposition between 0 and 1, and you cannot obtain the state when you do the measurement. So in that case, all the later phenomena corresponding to that laser will be also in this mixed state, like, so that the cat is also in this mixed state of alive or dead. Okay, so another interesting thing that we can use in the quantum computing is that it's called a Bloch sphere, and also it is very intuitive for us to understand the previous state, right? So for example, we have two free variables in the system right now, which is alpha and beta. And alpha and beta, we already know that they are complex values, right? And then we can actually extract this global phase to make sure, like, extract the global phase and remove the global phase, and then we can reduce the alpha beta to a real number, right? We can use the polar representation, and then actually, because the global phase is removed, so we only remain 3 free dimensions, right? And then for the third row here, if we are representing this alpha and EI phi beta in this cosine theta over 2 plus EI phi sine over theta over 2, and then we can find that actually the system has 2 free dimensions, because the alpha square plus beta square should be 1. So in that case, we can use a very intuitive sphere to represent the state of one single qubit, right? So the theta here will be the dimension between the state with the z basis, which is the top row, top column here. And then we also have another angle between this projection of this to the middle layer, and then there will be an angle between this and also the x basis. So that will be the phi. So in that case, if we just change the theta and the phi, we can know that actually this pole will point into all the possible positions on the whole sphere, right? So that's how we can intuitively or graphically represent the state of a single qubit. And then any of the single qubit state on the surface can represent a unique quantum state. So okay, so that's how we represent the state in the system. So we use this state vector, and also we use this Bloch sphere to better understand that. So you may ask, like, if that's just the information, maybe that's already pretty useful because we can store some information. But if we want to do some computation, we have to apply those operations, right? So that's how we approach this information, by applying those gates. So first of all the quantum gates are actually reversible. Reversible means that actually you can do this reverse of the operation matrix. So just a simple question: what is the simplest reversible gate in a classical computation? So in classical, right, we have like a NOT gate. We have this like a XOR gate, but XOR is not a reversible one, because we have 2 input and only 1 output, because we cannot reverse the 2 inputs according to the output, right? So and then what is the simplest one reversible gate in classical computation? Any ideas? It's a single qubit gate, a single bit gate. And if you apply that, then very close, very close. Yeah, NOT gate is definitely very simple. But another gate is identity, right? So we do nothing. We just have identity gate, and then we can have this according to output. We can know what is input because it is safe, right? So that's the simplest reversible gate in a classical computation. But classical computation, they are also rely on those irreversible gates. For example, the XOR gate, XNOR gate, the AND gate, right? So and all the reversible gates, they have a good formation that they can be represented as matrices or the rotations, of course, is a Bloch sphere. So just like this NOT gate, the NOT gate is definitely reversible because you can just apply another NOT to reverse and then obtain the original input, right? So the X gate can be represented as this matrix as 0, 1, and 1, 0. So, and also when we apply this X gate to a 0 state, what will happen? So intuitively, we apply this NOT gate to 0, which should obtain 1, right? So how can we know that mathematically? So basically, we can apply this X gate to this 1, 0 state, and if we do all the math here, we can know that the output will be 0, 1, 1. So remember that the 0, 1, 0, 1 actually representing the 1 state, right? So that's aligned with our intuition in classical computation. Where we apply a NOT gate, we can obtain this obtain the 1 from 0, right? So that's also similar to when we have this qubit 0 as the initial like 1 state here, and if we apply a NOT, so that's actually rotating 180 degrees on the Bloch sphere to another pole, right? So that is the representing the state 1. We also have some other very splendid gates, maybe that is maybe not very common in the classical computation. So that is the Y gate and also the Z gates. So what are their representations? So like the Y gates here, we have 0, -I, and 0, right? And also the Z gates here, we have the 1, 0, and 0, and 1. So X gate and Y gate and Z gate, those are Pauli gates, right? So the Pauli gates, they are very they can construct the basis for all the gates we may have. So basically during this inside this X and Y and Z basis, so we want to ask what is the what happens when we apply this Z gates, right? So Z gates may be not very familiar to the classical computation, but what happened when we apply this Z gate to 0? So you can see that it's still 0. It doesn't have any effect, right? But what happened when we apply the Z to the 1 state? So if we do the modification, right, 1, 0, 0, 1, and if another is 0 and 0, 1, we can know that the state will be 0 and -1. So that is actually -0, 1, right? So in that case, we are obtaining the -1, but that is actually not physically indistinguishable to 1. So that's why we are saying like the global phase is not distinguishable. And also another thing is the 0 and 1 state are the eigenstate of the Z matrix. And we are, if we are doing the computation in the 0 and 1 basis, say we do all the calculations in 0 and 1 and do the measurement on 0 and 1. So that will be called like the Z basis computations. So here we can see besides the Z basis, like the 0 and 1, we also have two another common basis like called the X basis and also the Y basis. So the X basis is actually represented as the plus and minus symbols here, and the Y basis the left and right. So it's a very strange symbol, but also representing like the locations of those axes in this Bloch sphere, right? So you can see that the X basis, they have this this plus as this one, and also the minus as another to the opposite to that plus state. So the X state will be 1 over square root 2 of 1, 1, and the plus state will be 1 over square root 2 of 1 minus 1, right? So another thing is that for the right and left, it's similar to the X basis and Z basis. We can know that the right will be 0 plus I1, over square root of 2, and left is 0 minus y1 over square root of 2. So to understand the spaces, it's very important to understand the later parameterized gates, because sometimes we can do arbitrary operations on the basis. So we have to understand what is the essential basic components of those gates. So besides this X, Z, and Y gates, we also have another very important gates, which is called Hadamard gates. So the Hadamard gates is represented as the 1 over square root of 2 of the 1, 1, and 1 minus 1, right? So the importance of that is we can use these Hadamard gates to create some superposition, right? So the superposition is pretty cool. So it's like say you have this coin. How can you rotate it on the table, right? So that's a small trick, and you can use a Hadamard gates to do that. So the way that we apply this Hadamard gates is that if we just do the computation of this H to the 0 state, and then we can obtain the plus state. And if we apply this H gate to 1, and we can obtain the minus gate, the minus state, right? So that means we can use this to create the superposition of 1 and zeros. So there are some other gates, as I said, we may use them as the trainable parameters if we want to do some further tasks, like some quantum machine learning task or some like quantum chemistry task. We are relying on those parameterized gates to give us a large design space to do all the information manipulations. So for example, we have the phase gate, where we just have a 1, 0 and 0 e to the power of 1 I theta. And also we have the S gate, and also the S dagger gate, which means it's the inverse of the S gate. So the most general gate, after we introduce those like specific ones, the most general gate actually is the U gates, where we have 3 parameters and can implement all the possible gates, right? We can see it contains the cosine theta over 2 and also multiple other parameters. So in total, we have 3 parameters to control this gate. And all the previous gates can be deducted from some specific parameter from this general gates. Like if we plug in this pi over 2 as theta and 0 as phi and pi as lambda, and then we can obtain the H gate. Also, if we have 0, 0 lambda to that, we can obtain the P gate. So that is an ultimate generalization for all the single qubit gates. Okay, so that's for just one single qubit. You can see that one single qubit is not a big deal because we just have this vector. So what is the interesting thing here? That happens when you really scale up the system. When you have multiple qubits, and then you can obtain this like exponential large size of this space, right? So the first thing I want to emphasize is that say on a classical computation, we have if we have 2 bit, and then we have 4 combinations like 0, 0, 0, 1, 1, 0, and 1, 1. So at one time, all the like memory cells in your cell phone, they only can be at one state. It cannot be any of the combinations between them. But actually, if you have qubits in your pocket, maybe not in your pocket, but on the cloud, and then you know that the qubits can be something in between, that we have both all the informations in both all of the states, like from the 0, 0 to all the way to 1, 1, and we can have the energy for all of the state. So we can represent the information for that state with this state vector. So the length of that is doubled because now we have 4 possible parts to allocate the total energy. And also another principle is that all of the information, they should also, the square of them should sum up to 1. So that's also the normalization principle that applies to all the multi-qubit systems. So say even if you have 1,000 qubits, and then those 2 to the number of 1,000 numbers, they should also have this this phenomenon where we need to make sure all of them add up to 1. So just like the 2 qubits, when we have multiple qubits, right? When we have n qubits, the state of them will be a Kronecker product between all of their states. Say if we have one state alpha and A and B, and then maybe if we are considering the joint state of those 2 qubits, and then there will be this B Kronecker product with A, right? And then we can obtain this B0, A0 all the way to B1, A1. And say if we have 3 qubits, and then the length of the system will be 8, right? Because we have 2 to the power of 8 in terms of the information vector length. So here we can give an example of this collective state. So say we have this Hadamard gates, as we just introduced previously. We have this Hadamard gates on each of the qubits, right? And then we can create this all entangled state. We can create this all plus state. Sorry, it's an all plus state, which is the 1 over square root of 8 of all the state will be 1. So that is the this 3 gates can create this very interesting, like equally like distributed state. And then when we have this this multi-qubit system, we want to ask what happens if we just apply one of our previously introduced single qubit gate to this multi-qubit system, right? So say we apply this X, and then that should be doing this flip this 0 to 1. But when we apply this X to a 2-qubit system, say for this Q0, we have Hadamard gates, and then for Q1, maybe we want to apply another gate. So what should be the mathematical equation for manipulating this system's state? So we can see that actually we just do a outer product between the 2 operations, between the X and H, and then we can obtain this joint matrix as the operation, and then we can apply this joint matrix to the original state of the Q1 and Q0, and then we can obtain the final state of that. So another example is that say we have this joint unitary matrix. Say if we just don't apply any gates on Q0, right? We just apply a NOT on Q1, and then we can also do the calculation of the joint unitary matrix of this all the operations applying on those 2 qubits. So that's similar to the previous one. We just have this canonical product between X and I, and then a very simple expansion to obtain the gates. Yeah. Okay. So here we have a very important multi-qubit gates, which actually generate another important important principle in quantum computing, which is entanglement, right? So we already introduced superposition generated by Hadamard. We also have this entanglement generated by the C0. So how exactly that is obtained? So we can see that actually C0, what is C here? C is controlled, and NOT is NOT gate, right? So C0 is controlled NOT gate, and essentially it's doing when the when the qubit 0 is 0, and then we are not doing anything on the Q1, right? But if the Q0 is 1, we are doing a NOT gate on Q1. So that's this NOT gate is dependent on the state of the Q0, right? So if we see the truth table for that, we can see that if the control and the target is 0, 0, and the final output will still be 0, 0. But if we have 1 on the control qubit and the target qubit is 1, then that would be a flip on the information for that target qubits. So if we are representing this C0 gate in the matrix representation, we can obtain the right-hand side information. We can see that the C0 is like 1, 1, and then we have an off-diagonal 1 and 1, right? So the interesting thing happens when we the interesting thing happens when we apply this C0 gate to previous together with the Hadamard gates, right? So that means say we have Q0 and Q1. What is the current state? That is 1 is the Q0. It should be the plus state because of Hadamard gates, right? And then the 0 should be still the 0 gate. So we can right now the joint state will be 1 over square root of 2 of 0, 0 plus 0, 1. And after applying the C0 gate, right? After applying the C0 gate, you can see actually the state will be not previous ones. It's not 0, 0 plus 0, 1, but this 1 will cause the flip of this 0, right? And this 0 will not change this. So we got the 0, 0 plus 1, 1, right? So that's the result after the C0 gate. So we have this C0 after this is this state. So this is a very interesting entangled state because the information or the energy always all concentrate on both 0 or both 1 state. So what is the what is the implication of that? So that is called like spooky action at a distance. So that means, say, if we created this entangled qubits here, and then one of you can bring it to another side of the galaxy, right? And then if we measure that the two qubits are together, and then we can always know that if I obtain 0, another people, that state will be also 0. So if that one is 1, the state of my qubit is also 1. So that is because the two qubits is already entangled. So they are always both 0 or both 1. No matter how large is the distance between them, they are still entangled, right? So that is something not explained by the physics yet, but we do have this experimental results that they have this like very unintuitive way of interaction along a very long distance, right? So that's why it's called a spooky action. So, but sometimes we may ask whether we can use that to do some super light speed of the communication, right? Whether we can use that to communicate with another people instantly. So the answer is unfortunately not. So there is a called no communication theorem. So that means when you measure the qubits, you know it's 1 or 0, but you don't know what is the you cannot convey the information because you don't know what is whether that's 0 and 1 ahead of time. So you cannot send even 1 bit of information through this. The only thing you know is that after you measure this 1, you know another people is still 1, but you cannot get any bit of information from another side, right? Because of the pure like stochastic behavior of these two entangled qubits. Okay, so just like we introduced, we are not able to do this measurement communication using this two entangled state. Okay, so another important phenomena is called like phase kickback. So the thing is that, say we have one qubit gates x here, right? And then if we're applying this x gate to the minus gate, minus state, and then we can obtain this minus of the minus state, right? And then if we're applying this C0 to the -0 state, we can obtain this -1 -0 state, right? So that's also the case for the C0 for the -1 state. We can obtain this -1 state, right? So what we're trying to say is that actually the C0 can add an additional phase on the control qubits, right? So similar, if we consider something like in the classical domain, so if we are using a bit to control another bit, so it's typically the original bit will not change, right? Otherwise, the control system will there should be some feedback to change the original one. But typically, if we are using some bit as a control bit, it will not be impacted. But however, here if we are doing the C0 on this minus and +1 state, we can see that the final result will be minus and minus. So that means actually if we apply the C0 and then the target is not changed, but the original control qubits is changed, the state is changed from plus to minus, right? So that's called like the kickback of the phase from the target to the control qubits, right? So that's a very important like subroutine in many of the quantum algorithms, including the one we introduced later. Okay, so just quickly on some of the other commonly used multi-qubit gates like the CZ and swap and CRZ gate. So they're also like basis gate we can apply on the quantum circuit on the qubits. Okay, I think we can have a quick break and we can come back in 5 minutes. And we'll continue to introduce the quantum circuit. Yeah.
That's really
okay, so let's continue. So we already introduced several basic operations in the quantum circuit. So we just have a very simple example here to show how can we construct some of the calculations using those operations, right? So the typically quantum circuit contains several different components. The first part is that we need to initialize the quantum circuit, and then, for example, we initialize the qubit 0 in some initial state, phi, and also maybe we want to initialize to 0 or some other state, right? And then we apply some of the quantum gates to all the qubits, say the Hadamard gates, the CNOT gates, and then we can do the measurement to obtain the final result. So sometimes we also have the classical base, like say if the classical one is 0, and then we can apply some further gates to the qubits. But remember that after the measurement, the state will collapse to either 0 and 1. And then we are using this information to control, we can use this information to control the remaining qubits. So some of the very complicated quantum algorithms contains this condition gates. So here we can have a very simple example, which is an adder, right? So because in the classical digital logic, we believe the first circuit we learn is the adder circuit. So how can we achieve that in a quantum circuit, right? So the first thing is that we need to keep in mind that the CNOT gate can do this A XOR of the B, right? Because if we're having those two A and B, if they are the same, and then we have this the output will be 0, but and then the input A will be keep the same. So in that case, we can already achieve a half adder using the CNOT gate, because if this is say we firstly do the inverse of the Q0, and then if this is 0, and then we do a NOT here to come to 1, and then that will do a flip of the first result here. And then the second bit here, we also do a flip, and then flip this qubit 2 here, right? So that will construct a half adder right now, but we don't have the carrier bit. So how can we do that? So actually, we can just simply apply 3 qubit gates, which is the CCX, which means if both of the Q0 and Q1 are 1, and then we do a flip on the Q3, right? So in that case, we can achieve this full adder using the several layers of a quantum circuit. So that's also resemble our previous introduction. So we have the embedding here, we have some quantum layers, and also we have the measurement. Okay, so because we already have this sense of how can we construct a circuit, what are the basic elements. So what is the current stage, or what is the most advanced quantum computers right now? So we want to introduce a little bit about the NISQ era. So that means the noisy and intermediate scale quantum. So the noisy means we don't have a very good quantum machines. So typically the error rate of them is 10 to the power of -3 or 10 to the power of -2. So here we can see a range of the a bar of different CNOT errors on the IBM's quantum machine, which have 127 qubits. And then we have the single qubit error of about the 10 to the power of -3 to 10 to the power of -4. So basically, we can see different colors here that also have a wide range of different performance among different qubits, right? So that is also very different from the classical computation. So say classically, when you do the computation, say on your laptop or on the server or on your cell phone, you don't expect the result to be different, right? But on the quantum, you have to very carefully select those qubits you want to use, because different qubits have very different performance in terms of the error rate, and also the gate time, and also some other characteristics. So as we said, there is a large gap between the algorithm requirements and also the device capacity of the device. For example, here we can see the x-axis is the system size, and the y-axis is the error tolerance, right? The error tolerance means how good is the operations on a quantum device. And we can see that among time, we are improving this from like 10 to the power of -1, like maybe 50% or even higher of the error, to around 10 to the power of -3, which means it's 1/1000 times of the error. So we increase 2 order or 3 orders of magnitude. And some of the recent device from Triple Ion, they already achieved the best available machine is around 10 to the power of -4. So that's what we are now. And also in terms of the system size, we also scaling from like 2 qubits to 1000 qubits in the recent several years. However, we can see there are several very high points on the top right corner. So basically, if we want to do some variational algorithm, maybe that's closer, maybe we have 1,000 qubits, then that's enough to achieve quantum advantage. But for those short algorithms to do the large integer factoring, that still require maybe 2 orders or even 3 orders of magnitude larger quantum machine. And also the error rate you can see is around, the requirement is around 10 to the power of -5. So in that case, we can see there is still 1 order of magnitude on this dimension and maybe 3 orders of magnitude on that dimension to achieve the final like holy grail of the quantum computing advantage. So there is a gap between the available machine and also the quantum device. So we our like quantum computer architecture and system people try to better try to solve this gap. Say maybe we can close this gap by a little bit by innovations and also optimizations on the system level. Some of our previous work trying to say if we are doing some noise mitigation on the quantum device, we can improve the device error rate by several x. So that means we don't just wait for better and better device from the hardware vendors. Right? Just like you don't just wait for NVIDIA to have a next generation of GPU, you also do optimizations of the models, right? So in that case, we also have on another dimension, we also have the system size. So previously, say if you just have a quantum machine with 1,000 qubits, but maybe you can only use 100 of them, because when you are using more of them, then the final result will be very erroneous. But our technique also focus on how to better fully utilize the current available machine. So one of our previous work, Quantum Labs, trying to find that some of the device, if we are designing very device-specific algorithm, we can better leverage available qubits. So we just so that in this system level and architecture level innovation, we can bring a better scaling and also faster reach to those large algorithm requirements. So one of the most core or the most popular problem in the quantum machine is called compilation. Is called qubit mapping. So intuitively, what is the qubit mapping task? So that is like, for example, we have a quantum machine with 5 qubits, and those qubits, they have some connectivity. They have some connections. Say between the P0 and P1, we have an edge, right? And between the P1 and P2, there is also edge. So we have 6 edges in this graph. Each of the edge means that we can do some operations between those 2 qubits. So then we can have a look at the quantum circuit here. So we can see there are some single qubit gates, but there are also some 2 qubit gates, right? Between the Q0 and Q1, we have the 2 qubit gates. And also between the Q2 and Q3, we also have 2 qubit gates. So that should be very simple on this topology, because we can directly apply using the E1 and E3, right? But what happens when we want to apply a gate between Q0 and Q3? So that may always the case for algorithm people. They don't during the algorithm design, those people don't consider the actual topology, right? So in that case, we can find between Q0 and Q1, there is no physical 0, 1 and physical 3, qubit 3, there are no connections. So how can we do this calculation? So one way is that we can do some swap, like swap the information between P0 and P1 using this gate, right? So the swap means after this, the qubits will be the information on qubit 0 will be on qubit 2, and then qubit 2 will become qubit 0. So that's just like a physical or like logical information-wise swap between those 2 qubits. And then we can do this desired gates between Q0 and Q3, because we already have the direct connections between them, right? So here I want to just have a small introduction of the subray qubit mapping, which is the standard or the default mapping if you're using IBM quantum machine. So if you're constructing any circuit and then give some topology map, and then you are using this subray qubit mapping. And this qubit mapping depends on a small greedy algorithm, heuristic. So that means, say, initially we have some, we can map those qubits randomly to the circuit. Maybe just according to the index here, I just map Q0 to P0, right? And then Q1 to P1, and all the way for other qubits. And then So here is the basic algorithm. So the basic idea is that say we can firstly do all the gates we can do, and then maybe we find one gate which is between 0 and 3, and we cannot do that. So there will be a iteration of all the swaps that can be done, right? For example, here we can swap 0 and 1, 0 and 2. We have 6 different different kinds of solutions or candidates to do the swap, and then this swap subgrid algorithm will find will go through each of them, right? Go through each of them, and then say if I update, if I apply this swap between 0 and 1, and then I update them. So that is this line, like I update the qubit mapping with this swap, and then we'll compute a score for that swap. So what is how the score is calculated? So the intuition is that, say after this swap, how many later gates can I apply, right? For example, if the ideal case is that, say after this swap, all the remaining gates can be applied with no problem, right? But the bad case is that after this swap, we still cannot do any gates, because say 0 and 1 swap, it doesn't solve the problem between 0 and 3, right? But if we do the swap between 0 and 2, and then we can do multiple gates later. So there can be a heuristic function, a heuristic score that we assign to each of the swap in the design space. And then according to the swap, according to the score, we can find the one with the best score, like the minimum score here. Minimum means the cost, or you can consider that as the best swap. And then we can update that, and then apply all the gates later, and then we can do this again. So that's the basic greedy algorithm that we are many of the existing compilers are using. So, but remember that the initial state for this is that we need to do the initial mapping randomly, right? But we found that sometimes the initial mapping will be very important for the overall performance. So here is another follow-up technique to do the initial layout using subgrid. So that means, say I have this initial mapping, right? And then I have this fancy quantum circuit gates. And then I can use the previous way to insert all the swaps. And then we obtain the final mapping, which is each qubit is on which physical ones. And then we are leveraging the reversibility of the circuit. Say, because we know this circuit should, if we reverse them, and then just like this, and then all the connections should resemble the previous sequence, but just reversed. So if I remove all the swap gates we insert in between and just use the reverse circuit and use this mapping to do the subgrid again, and then we can obtain the initial mapping, right? And then we just start from initial mapping to do the mapping again. So we can actually, because we have this reverse and the original circuit, these iterations, we can do many rounds. So each round can improve upon the previous mapping. So that's all using this phenomena of this reversibility of quantum circuit. So it's a very elegant way to find the best initial mapping, right? So because we can do this for many iterations. And also another thing we are developing is that for the initial mapping, actually probably we don't have to do this for using just reversibility. We can use some evolutionary search engine or some other machine learning based method to help us to find the initial mapping, right? So in our previous work, Quantum NISQ, we actually trying to find this initial mapping. So basically we have many different candidates. Like say you map qubit 0 to qubit 10 or physical qubit 10 or some other different mappings. And we have some different candidates. And we are using this, we have a search engine to generate the mapping candidates and to evaluate those on the actual quantum hardware, right? And then we can obtain this noisy feedback to know which mapping is good or not. And then we can update the candidates of the inside the search engine. So that is the part of the Quantum NISQ work trying to solve. Okay, so and finally, I want to just give an intuitive understand how we are using the superconducting quantum device to execute all the circuit we just introduced, right? So first of all, we have this classical laptop, right? We do all the programming and also all the construction of the circuit in the high-level language, say maybe in a Qiskit or in a Torch quantum, and then we can say we write this QC.measure. That means we want to do measurement on qubit 0, and then maybe we want to apply some gates. So after this construction, So this circuit is sending is being compiled and then sending to the classical server to do the hardware signal generation. And then we send this signal all the way down to the quantum machine from this. This is called like a dilution refrigerator. So that means you can have a really low 4 millikelvin of the temperature down to the chip. And we send the signal down to the chip, and then we can obtain the measurement. We can obtain back the measurement outcome from the qubits and all the way back to across the stack, and then we can obtain the classical 0 and 1 from the system. Right. So here are some like basic components, like the for example, some of them are some of amplifiers and also some of signal generators. And then this is classical computer. We send the signal all the way from the 300 Kelvin to a very low, like 4 millikelvin or even lower to the qubits here. And then we can send back the information back to the classical computer. So here is actually a detailed information about the control signal we are generating for each of the qubits. So here we can see that there is a omega LO, which means it's a carrier frequency, right? And then we also have the arbitrary wave generator to generate the actual control shape. Sometimes it's an envelope. Sometimes also have a small frequency omega AWG here. And we also have the ST as the envelope of the control shape. So, and then we have this mixer to mix this basis frequency to this generated pulse signal together, so that we can obtain this desired qubit control frequency, which is omega IO plus or minus of the omega AWG here. And also the envelope will be the same as the baseband pulse envelope. So and the carrier's frequency is always similar to the drive frequency of the qubits, so that we can resonate with the qubits to change the state. And also here we can see these are several different gates, like the amplitude of Y is like this, and then we have X gate and also Y gate, X gate. So different, say for the rotation of the pi over 2, we can see that the shape or the area under curve is smaller, and for the rotation of pi, the area under curve is larger. So the degree of the rotation of the angles is actually determined by the area under curve for this specific superconducting device. For some other, like trapped ion or neutral atom, they have different control signals. So here, the basic workflow is that we just construct a circuit, and then we can do the compilation, right? For example, some of the gates will be constructed this two shapes. Actually, this is one of the rotation 90 degree, and also virtual Z gate rotation 90 degree. So this part is the X gate, and then we have two cross resonant CR gates to construct the X gate, C naught gate, right? So you can see they are sometimes not very easy to correlate it, because this is just like you are writing Python. This is like you are writing assembly code, right? So from the assembly code, it's very difficult to understand what is exactly the previous gate, right? But we have to do this because the underlying device can only use this basis operation to do the computation. And then finally, we can do execution and obtain the final measurement outcomes. So just like the single qubit control, we are saying that we are doing this pulse wave, and for many times it looks like a Gaussian, but actually it's a small variance of the Gaussian, which is called a drag shape. And then we are using this shape, and the actual area under curve will determine what is the rotation angle we are doing. So, for example, if we are having a very large angle, right, and a very large amplitude, so we are rotating more degrees on a sphere, right? If we have a small, and then we are rotating a small one. So it's just like you are sending the signal, and the qubits will rotating on this sphere until the target location. Yeah. So in terms of the 2-qubit control, is a little bit more complicated. But for the IBM superconducting device, if we're doing just like the shape here, if we're doing this two I-code cross resonant gates, actually there are multiple different terms in this Hamiltonian. And the one we want is the ZX term, and for the others, there are some techniques to remove them during the calibration. So that's how we can transpile this high-level gates to the low-level control pulse signals. And finally, we have this this overall of the circuit. Say have this circuit, and then that will be translated to the overall all the control shapes on all the channels of the quantum device. And then we can send this all the informations to the quantum hardware to apply the corresponding computation. Okay, so today's lecture, we briefly introduce, motivate why we are using quantum, which have the potential for the ultimate solution of computing power, and what is the basic operations for those single qubit gates, multi-qubit gates, and how can we do this holistic computation using some quantum circuit that contains encoding, computation, and measurement. And also we are introducing what is the current status, right? We are in the noisy intermediate scale quantum era, and we still have a lot of compilation problems that requires the architecture and system people to solve. And finally, we introduce what is the physics, from the physical perspective, what is the whole workflow of the superconducting IBM device. So actually, here are the reference. So if you are interested, you can actually just register an account from IBM's quantum open platform, so you can get free access to all the quantum device and play with them. So with that, thank you for coming.